Good afternoon, everyone. So I'm Michael Marcozzi. I'm a postdoc at Imperial College London, and I will present you this paper that is actually been published at the OOPSLA conference. And this is a joint work with Chi, who's at Oxford, with Ali, who's mainly in Google, but also a bit at Imperial, and Christian, who's totally at Imperial. And so, I will start immediately by giving you the context of this research, which is actually compiler fuzzing. So software developers rely quite intensively on compiler in their everyday work, and they do that often with some kind of a blind confidence. But in practice, compilers are nothing else than software, and like in any piece of software, you will find bugs in compilers. And for example, if you have a look, doesn't work, on this graph at the bottom of the slide, it's actually a history of the LLVM bug tracking system from 2003 to 2015. And if you have a look at the blue line there, it shows that there are more or less 150 bugs that are fixed each month in the well-known LLVM compiler. And so, when you have a bug in a compiler, it can just be the compiler which crashes during compilations, which can be a bit annoying, but it has not that big consequences. But in the worst case, what happened with a compiler bug is what we call an unnoticed miscompilation. So the idea here is that the compiler will silently generate wrong binary code that you will then execute as a part of your application in production, making the application possibly fail in production with possibly really bad consequences. And so in order to avoid this, there have been a lot of work to apply all the classical software validation approaches to compilers. So there have been a lot of formal verification, notably with this ComCert initiative, which has been very successful in designing compiler which is verified by construction using some kind of formal proofs, and the compiler is for a subset of C. There have also been this alive optimization prover. So what they do there is that they have a language to encode optimization for LLVM IR. And they have also a tool that can prove if an optimization is right or wrong using an SMT solver. And the tool can also, if the optimization is wrong, it can detect the bug and provide a counterexample. And by doing that, they've been able to report 8 bugs in LLVM. And of course, there is also a lot of testing of compilers. For example, for C, there are several C test suites which are commercial. But also, main compilers have their own test suite, like the LLVM test suite, which contains a lot of big and well-known programs, together with their own regression test suite of LLVM developers. And among compiler testing techniques, there have been recently a surge of interest in a particular technique called compiler fuzzing. And so what's the idea of compiler fuzzing? So actually the first point is to generate automatically a massive number of random test programs. And then each of these programs, which we will call P, is fed to the compiler. And compiler fuzzing provides a way to automatically detect if the program P was miscompiled by the compiler. And this is done either with some kind of a differential testing or metamorphic testing. So with differential testing, the idea is that you take your program, you compile it with n different compilers. You will obtain n different binaries for the same program. You run the n binaries, and you record the outputs of each binary. And if your program was totally deterministic and well-defined, you should have the same results. And if it's not the case, it means that at least one of the n compilers is miscompiled the program, and you have detected a bug there. For metamorphic testing, the idea is a bit different. So you take your program P, and you create a variant of P, which we call P prime. And for example, what you could do, the idea is that actually P and the behavior of P prime should be predictable given the behavior of P. So for example, what you can do is just, you take P and you remove some parts of dead code. So you know it's dead code, you remove it, so that the two programs are different, but their result should be exactly the same as you have just removed dead code. And then what you do is that you compile and run P and P prime and check that the outputs of P prime are what you expect they are compared to the outputs of P. And if it's not the case, obviously you have also found a bug. So for example, if you have removed that code in P prime and P prime returns a different results from P, probably there is a bug in your compiler. And by using this compiler fuzzing approach, there have been notably more than 200 miscompilation bugs that have been found in the LLVM compiler by the four main fuzzing tools, which are CSmith, equivalence modulo input, which we call EMI, Orange, and Yabgen. And so, so this was the context, compiler fuzzing. And so what's the problem now? The problem is actually the importance of the miscompilation bugs found by fuzzers is actually quite unclear. So when we give talks about compiler fuzzing, the audience will often question the importance of the bugs that have been found by the fuzzer, notably asking, yeah, couldn't you improve your fuzzer by taking inspiration from real bugs found by real user compiling real code with the compiler? And actually, in our experience, this question of the importance of fuzzer-found bugs is a contentious debate where people can really be poles apart. So for example, if you look at the greenish sentence there, it was actually a comment from one anonymous reviewer of the paper that I'm presenting now at a top programming language conference. And the reviewer said, in my opinion, compiler bugs are extremely dangerous, period. Thus, regardless of the real-world impact of compiler bugs, I think that techniques that can uncover and help fix compiler bugs are extremely valuable. And in the other end, if you go on the well-known Shape of Code weblog, you can read this reddish quote. I would suggest that compiler developers stop responding to researchers working towards publishing papers on fuzzers. Responses from compiler maintainers is becoming a metric for measuring the performance and fuzzer, so responding just encourages the trolls. So yeah, you can see it's quite contentious. And given that, in this work, we have chosen to consider a mature compiler in a non-critical environment. So if you have a mature compiler, you know that it has been intensively tested by both its developers and end users. And if you are working in a non-critical environment, trade-offs between the reliability of software and the cost to develop software are actually acceptable and even quite common. And in this context of a mature compiler in a non-critical environment, doubting the impact of fuzzer-found bugs is, in fact, reasonable for at least two main reasons. The first one is that it's unclear if in a mature compiler you will be able to find enough space to find severe bugs, as maybe all the severe bugs will have already been found by this intensive testing by developers and users, so that the only bugs that would remain would be, quite mild bugs. The second reason is that fuzzers actually find bugs that will affect the code that they generate. And if you have already looked at some generated code, quite often it feels really artificial. Nobody would have probably ever written that. So that it's a question if the patterns in which the bugs have been found by the fuzzers will actually occur in real code, so that the bugs would trigger also on real code. And our goal in this work is to provide a study of the practical impact of miscompilation bugs. So more precisely, what we don't want to do is to show specifically that compiler fuzzing matters or does not matter, but first, to study the impact of miscompilation bugs in a mature compiler over real applications, and then to compare the impact of the bugs depending on the fact that they've been found by a fuzzer compiling artificially generated code, or by other means, and notably bugs found by real users compiling real code, real applications. And more practically, what we are aiming at doing is overcoming the two following challenges. First, take steps towards a methodology to measure the impact of a miscompilation bug, and then apply this methodology over a significant but still tractable set of bugs and real applications. And yeah, in the two next section of this talk, I will present you our methodology, and secondly, I will show you how it has been applied on real bugs and real applications. So let's start with the methodology. So as a first assumption, we have chosen to restrict ourselves to bugs in open source compilers which have been publicly fixed. And this enables us to extract the fixing patch for the bug, which has been written by the compiler developers. And together with this fixing patch, we can also extract the source code of the compiler just before the patch was applied, which is what we call the buggy compiler source code, and the source code of the compiler just after the patch was applied, which we call the fixed compiler source code. And as a second assumption, we have chosen to liken the impact of a miscompilation bug to its ability to change the semantics of real applications. And given these two assumptions, we estimate the impact of the compiler bug over a real application using a three-stage methodology. So first stage, we check if the buggy code in the compiler is reached and the bug is triggered when the application is being compiled. If this happens, then at stage two, we measure how much the fact that the bug is triggered will change actually the syntax of the binary code which is produced by the compiler. And if there are such changes appearing in the binary code, during the third stage, we check if these changes can lead to differences in the runtime behavior of the binary produced by the compiler for the application. And so now I will give you a bit more explanation about each of these steps in more details. So let's have a look first at stage one, which is the compile time analysis. And so here you have an example of a real bug in LLVM, which is bug 263223. And so on the left here, you have actually the section of code in the buggy compiler, which is actually affected by the bug. So what do you have here? It's just an if statement. And if the condition is true, the compiler applies a transformation to the code that it is compiling, actually. And the bug is that the condition is not strong enough, so that it might happen that the code transformation will be applied mistakenly, leading to the code being, in the end, miscompiled. And so what was the fix for these bugs developed by the LLVM developers? Basically, they just have strengthened the if condition, and they have added this here, this second part of the condition, so that after the fix, the code transformation will only be applied when it is legal to apply it. And so what we do in this stage one is to write a third version of the compiler, which we called the warning-laden compiler, which is actually a modified version of the fixed compiler source. So we take the fixed compiler and we modify by hand its source code so that it will print warnings when the fixing patch is reached and the bug is triggered. So you just add basically a warning just before the fixing patch, before the fixing patch to say that it has been reached. And then for the bug triggered, when will the bug be triggered? But simply when, in the case where the code transformation will be mistakenly applied by the buggy compiler. And this will happen in the case where the original if condition is true, but the second one is false. And so this will happen if the original condition is true, but the added condition here is false, so that the buggy compiler would apply the transformation and the fixed one would not. And there you print this bug triggered, you added this bug triggered warning. And when you have crafted by hand this warning laden compiler, you just take the source code of your application and you compile it with your warning laden compiler. Of course, you will get a binary for this application, but also you will get compilation logs. And you just grab the logs for your two warning messages. And if you find these messages in the logs, you know that the fixing patch has been reached and the bug triggered during compilation. And if this happens, you switch to stage 2, which is the syntactic binary analysis. So here again, you take your buggy compiler, your fixed compiler, and the source code of your application, which you will compile with both the buggy and fixed compiler. And this will give you two binaries for the same original source application, one produced by the buggy compiler, one by the fixed compiler. And then what we do here is simply to check, to disassembly the two binaries and check for syntactic differences in this assembly code. That would have been caused, obviously, by the compiler bug. And how do we do that? Simply, we just do a textual comparison, opcode by opcode, between the assembly code produced by the buggy compiler and the one produced by the fixed compiler. The idea is that it enables us avoiding a lot of false positives. For example, you know, if the register allocation is a bit different between the buggy and the fixed compiler during the process, you would have different registers, but it would not change the semantics of the two binaries. And so you would end up reporting a lot of differences that are not meaningful. And so that's why we just only compare the opcodes. The drawback of this is that, for example, if the compiler bugs would affect register allocation, you wouldn't be able to spot it if you just compare the opcodes. And so you would have false negatives. But with the bugs that we have considered in these studies, we have been able to observe that they were always affecting the opcode in some way. And so, yeah, you know, we are sure that we don't have false negatives in this case. Yeah?
If the bit is not deterministic, you may have other changes. Does this happen?
Yeah, I've not explained it during the talk because otherwise it would have been a bit too long. But actually, we work with Debian packages, and actually they have a whole process to make sure that the build process is totally deterministic. And so we have only selected the packages which fulfills this criterion, and we have tried to compile them several times to be sure that there was no non-deterministic builds, so that we are sure that the difference can only be caused by the compiler and not by anything else. Thank you. So if we spot such differences, actually we go to stage 3 to do this dynamic binary analysis. So the idea is that we keep the two binaries, the one produced by the buggy compiler and the one produced by the fixed compiler. And for each of them, we run the test suite of the application. And we check for cases where actually a test would fail with the binary produced by the buggy compiler, and would succeed with the binary produced by the fixed compiler. And this would indicate that actually the test is failed because of a miscompilation by the buggy compiler. So actually, it seems simple, but actually it's quite tricky for at least two main reasons. So if you have a test divergence between the buggy binary and the fixed binary, it does not necessarily mean that you have a miscompilation, notably because you can have flaky tests. So it's really well known that test suites are not perfect, and sometimes a test can non-deterministically fail or succeed. And so you need to take this into account and try to check if the reason of the failure of the test is flackiness or it's a real miscompilation. And the other problem is that if you don't spot any test divergence, it does not necessarily mean that the buggy compiler is not miscompiled its binary. It can just be that the test suite is not strong enough to expose this miscompilation. And in order to alleviate a bit this problem, we've tried to do a bit of manual inspection. So what we've done is that we have selected a sample of the syntactic difference between the assembly of the two binaries that we have observed in stage 2. And for each of these syntactic difference in assembly, for example, this one, we have used tools like GDB-GUI to find which line in the source code led to the two compilers generating different assembly code. So for example, you could establish that this is line number 12 that led to this code being generated by one compiler and this one by the other one. And given that, we have tried to understand by hand, actually, what happened, why was this line compiled differently by the two compilers. And once done, we have actually tried to craft manually either local or global inputs that would trigger a runtime divergence when executing these two codes, so that this one would produce one behavior at runtime and this one another one. And this would lead to a better understanding of these differences and how they can impact the semantics of the application. So that was the methodology. Now I will give you a more explanation about the experiments and results. So what we have done is basically to apply this bug impact measurement methodology over a sample of 45 miscompilation bugs in LLVM. The bugs were found only in translation from C, C++ to x86-64. And among these 45 bugs, there are 27 fuzzer found bugs, which represents a sample of 12% of all the miscompilation bugs that have been fixed and found by CSmith, EMI, Orange, and Yabgen. And also we have 10 bugs that were detected by end users compiling real code, and the 8 bugs found by applying this live formal verification tool over LLVM. And during our experiment, we apply this bug impact measurement methodology to evaluate the impact of these 45 bugs over 309 Debian packages, which are totaling more than 10 million lines of C and C++ code, which have been selected so that they are not part of the LLVM test suite, and they represent a diverse set of applications with respect to type, size, popularity, and maturity. And examples of such packages are Apache, Samba, and grep. And so after a lot of manual effort and more than 5 months of computation time, we have obtained the following results. So here you can see actually the fraction of package builds for which the patch is reached at stage 1, the bug is triggered at stage 1. We get different binaries from the buggy and fixed compiler at stage 2, and we observe a test divergence at stage 3. And so in blue, you have the aggregated results for all the 27 bugs that were further found. In green, the results for the 10 bugs affecting real code. And in orange, the 8 formal verification bugs. So what we have observed, more or less, at stage 1 is that more or less all but finding approaches discover bugs that are actually quite frequently reached when compiling real code, and that are sometimes triggered in this case. Then if you have a look at stage 2, you see there that, when you look at the binaries produced by the buggy and fixed compiler during the package builds, you will only find different binary for a small fractions of these package builds. And actually, if you look then at, for the packages which are different, which part of the code is affected by this difference, only a really teeny number of package functions are touched. So on this graph here, you have, for each bug here, you have the number of functions in the whole set of 309 packages that are affected by a difference in the assembly code. And so you can see that for the most impacting bugs, you reach 5,000, but in most of the time it's less than 100. And in total, for the whole set of 309 packages, you have a total of more than 200,000 functions. So it's only a really small fraction, which is typically touched by this difference in the assembly code. And so now we can have a look at stage 3, actually. And here you can see that the miscompilations caused only 3 package test failures. So there was 1 test failure in the ZSH package for the bugs found by Fuzzers, and 1 test failure in the LevelDB package for one of the bugs found by real users compiling real code. And we made also an extra experiment with SQLite, which was not part of our list of 309 packages. And with this experiment, we found 1 extra test failure for one of the bugs found by the Fuzzers. And so to give you a better understanding of what happens actually in practice technically, I will show you what the test failure looks like and what the miscompilation looks like for the case with SQLite. So actually the miscompilation here is caused by LLVM bug 13326, which has been found by C. Smith. And so what is this bug about? So actually the bug affects the translation of 8 bits unsigned integer divisions from LLVM IHAR to x86. So when you have this udiv LLVM IHAR instruction, you want to compile it to x86 binaries, there is a bug. And the bug is that when the divisor of the division is constant, the translation is wrong for 6 out of 65,000 possible divisor values. And this causes in SQLite the following line of code to be miscompiled. So yeah, actually what do we have here? So you have this element of an array, which is given the value here, which is also an element of an array. And so what you must do is compute the value of the index of the array. And actually, this value is known at compile time because this is 79. So that at compile time, the compiler can compute that this is 78. And then it must generate the code for the modulo 78 here, which end up being transformed into a division by a constant, which is 78. And the code which is generated, the x86 code which is generated for this is actually buggy because of this bug in the compiler, which will generate wrong x86 code. And then when you run the test suite of SQLite, for one test, basically the test will reach this point in the code with the value of this here, being 232. And you will have to compute the modulo of 232 by 78. And this code here, computing that, is been miscompiled, so that this will return 254, so that, you know, Z source 254 is out of range because the size of Z source is 79, and this is garbage. So that garbage value is given to this, and the whole test actually fails. So that's how it looks in practice. Yeah. So given this, the question is, why is there only three test failures? It's not really such a big number. So one reason could be that it's due to very weak test coverage. So in order to check this, we have taken a sample of our package test suites, and we have measured statement coverage. And actually, we have obtained 47 average statement coverage, and for half of the suites, we got more than 50% statement coverage. And also, we have done this additional experiment with SQLite because we knew that the SQLite test suite is very strong. It covers 98% of the statements among the 150,000 lines of code of the application. And yeah, so it looks like that this stuff indicates that it cannot be only that the test suites are very bad. And also, what we have done is to do this manual crafting of test inputs to understand better what these miscompilation bugs are. And so let's have a look at what we got. So basically, we inspected about 50 differences in package assembly code. And for each, we tried to craft inputs that would trigger a runtime divergence between the code generated by the buggy compiler and the fixed compiler at the point where there is a difference in the binary. And in all cases, we failed finding such inputs. And our conclusion has been that actually the difference that are present between the code generated by the buggy compiler and the one generated by the fixed compilers have little or no impact over the semantics of the package, often for two main reasons. First is that the compiler developers are often quite conservative when fixing a bug. So typically you have, for example, this bug 29031, where you know there is this optimization, which is buggy in a very, very specific case. But what they do is that they are very conservative and they deactivate quite the whole optimization, or in most cases, not only case where we know that it's buggy. And so that when you get the buggy compiler and the fixed compiler that produce different code, different binary code, it does not mean that the code from the buggy compiler was wrong. It's just that in this case, the optimization was correct, but as it was so that the optimization will be activated in the buggy binary and not in the fixed binary, and that you will see a difference, but actually the optimization was legitimate in this case, and so the buggy binary is not buggy when this happens. And a second case is that specific runtime circumstances are often vital for the miscompilation to have really impact over the visible behavior of the binary. And for example, you have this bug 27392, which actually affects loop unrolling. So it's an optimization where you unroll the loop. And actually the optimization will create so the binary code generated by the compiler will only be buggy in case where the loop will iterate more than the maximal integer that you can represent in an unsigned variable. which is actually very unlikely in practice. In most cases, loops are bounded by a reasonable number of iterations, so that, you will have a lot of cases where you will spot differences because many loops have been enrolled in this way, but most loops will only loop a small number of times, and so that you will never see the impact of the bug, of the miscompilation. So given this, we can switch to our conclusions. So our two major takeaways are that miscompilation bugs in a mature compiler will impact quite infrequently the reliability of applications in the wild, at least as we have probed it using test suites and our manual inspection. And they seem to have more or less a similar impact, no matter the fact that they've been found by a fuzzer compiling generated code or by real user compiling real code. And a possible explainer for these results is that in a mature compiler, all the bugs that will affect patterns which are frequent in real code have already been fixed because they've been found by this intensive exercising of the compiler by both the developers and users, so that there remain only corner case bugs, which will affect real and generated code more or less similarly, actually. And so to finish the talk, let's talk a bit about the future. So the three main research directions that we have in mind for an even better evaluation of the impact of compiler bugs is first to try to even better detect that a miscompilation is occurred in the produced binary, because we're doing that with the test suites and manual inspection, but we think that we can do even better. And one idea would be to use a technique called symbolic execution to go and target really the parts of the code where the binary code is different between the buggy compiler and the fixed compiler, and target really this zone in the code, stress it quite a lot, and try to detect a miscompilation using an oracle, which is a technique which we call multiversion execution, which will compare the system calls issued by the two binaries, actually. A second research direction is to exploit our methodology and artifacts even more. So people could do a replication study of what we've done. They could study more bugs. And they could also study, using the same methodology, other compilers, and notably less mature compilers, where we could get probably different results that we get for a mature compiler like LLVM. And finally, one thing which would be interesting is to consider the impact of compiler bugs on non-functional properties. So here we have only considered the impact of the compiler bug over the reliability of the application, but it could also impact the speed of the application and also even the security, because there have been some proof of concept showing how you could use a compiler bug to introduce a backdoor in the binary of an application. And so, yeah, it would be really interesting to have a better idea of how realistic this scenario would be in practice, because it could be really also a good, strong impact for, it could have a really strong, could give compiler bugs a really strong impact if it's a way to easily hide backdoors that are really hard to find in the code. So yeah, thank you very much for listening to the talk. So our research paper is totally open access. You can download it for free, and you will find a lot of details that I've not had the time to give to you here with this 45 minutes. Actually, our infrastructure is totally reusable. It has been tested by other people who have given these nice badges saying it's reusable, and you can download it also for free. So if you have liked this talk, just don't hesitate to have a look at my website and follow me on Twitter. And now it will be my pleasure to answer your questions. Thank you.
If you can wait to have the microphone if you have a question, so we can record it as well.
So this is very interesting. So basically, if I understand correctly, you found that in mature compilers, it doesn't matter where the bugs come from, because most of the bugs are irrelevant for them, essentially, because for real-world use. I'd like your talk about, your ideas about immature compilers, because basically people out there building lots of new languages as well, right? Where they're just building translations, not necessarily into machine code, etc. Do you have an intuition of whether compiler fuzzing is useful to sort of build up that initial test suite really quickly to a useful degree, or whether it's actually going to produce there, in those cases, a lot of bugs that are not really relevant for real-world use?
Yeah, it's. I don't know if it has been, if it can be used for, for making a test suite from scratch for a very young compiler. What I know, however, is, for example, one of the guys who's now working in Google, which has done the paper with us. Actually, in Google is doing fuzzing of graphical driver, a compiler for OpenCL. And these compilers are actually quite young and full of bugs, actually. And yeah, he made a startup with that. The startup was bought by Google, and yeah, now he's in Google and he's doing a lot of work to find bugs in OpenCL compilers and make them really much stronger than they've been for now. So yeah, given that, I would say that fuzzing can be, I think, quite efficient in this case. But yeah, maybe also having at least a basic test suite made by hand or this kind of stuff will also be very good to find, a first bunch of bugs. But I think fuzzing is very interesting there because most things are automated there. You get very quickly a lot of very small chunk that makes your compiler go wrong, and it's quite useful.
Yes. Well, thank you for quoting from my blog. I'm pleased to see I'm having an impact. Part of the background of what I said, my background is compiler writing. And in the commercial world, it's very difficult to get people to pay you to work on compilers. So the one way to get people to pay you is to say, well, if you pay us maintenance fee, I'm no longer in the compiler business, then we'll fix bugs for you. And of course, the other thing that's important in the compiler business is reputation. So if academics are reporting all these bugs in the compiler, it hurts your reputation, so you have to fix them for free, which is terrible. I was very interested to see how few packages were impacted by bugs that had been fixed. So this is the first time I've seen evidence. I know from practical experience this is true, but it's nice to see some evidence here. So I'm going to tweak your conscience here and say, well, what are your views about academics running fuzzers and then expecting people to fix them for free?
Yeah, I think that, indeed, there's two sentences in the beginning of the talk. I think indeed they reflect different views that are, when I think the academic there was some guy working in theoretical programming languages, and so, in this world, you would like that all software be full of bugs, without any bugs, and really perfect for the good of humanity. And if you are working and making a living by making a compiler, what is important to you is way to make money and to survive. And I think that was what was at stake in these different views actually. I think. For compilers, maybe like GCC or LLVM, the guys who have reported bugs in, the guys who have written these papers about compiler fuzzes, actually they've reported bugs in many compilers, but quite quickly they've realized that they had only answers and interest from the guys from LLVM and GCC. The more proprietary ones and this kind of stuff, they had less interest. And maybe I think it's linked to the fact that, I wouldn't say that GCC and LLVM are just made for the greater good and there is no commercial interest in there. But still, they are they are open source, they are free, and so, it's just these stuff are there for the greater good, and so you can have in mind that your goal by doing this compiler is to avoid bugs for the greater good, and avoid that one day because someone compiled his application with your compiler and there was a bug in it, someone would die because of that, or would have a problem. And so it's more, this question which is interesting. So I think, I think compiler fuzzing, I think the fact that academics are reporting all these bugs, I think it's meaningful, and that's why GCC and LLVM developers are tackling them. Yet, if you are more in developing a proprietary compiler, then indeed, maybe your criterion for solving bugs is to satisfy your customers. And there, I can understand that you say I don't care about fuzzer bugs. So I think that's more or less the idea. Then it's true also that, as you said in the blog, academics went maybe a bit too far and reporting everything and using that as a benchmark for their papers, without realizing that there are real people doing real work behind it. And so I think it's more a matter of people having different interests, different view of the world, and that's why this happens. But I think it's interesting fuzzers can be interesting tools to use, but it will really depend on the people interests at that moment to fix the bugs or not.
Thank you.
Hi, nice talk. I'm curious about the differences that you would see if your both input language and the output language changes. For example, in the example you showed, from the source C program to the generated assembly, the difference isn't that great. But I'm assuming what would happen if you, let's say, compile to a higher level, lower language, let's say to bytecodes. If you compile the same kind of programs to bytecodes, would you see more bugs or less bugs? Or if your input languages change from, let's say, C to Haskell, do you think there would be more bugs or less bugs? Any opinion on changing both the source and the generated output?
I think this will be linked to probably the maturity of the tools. Actually, if you are trying to compile from an obscure source language to a totally obscure platform that two people in the world have ever activated this stuff, and the developer said, okay, we will test that one day when someone will complain. Quite probably you will find a lot of bugs in that. If you go for something which is very, very popular and a lot of people would complain if a little bug would happen, probably there you will find much less stuff. But obviously, the more layers you add, the more chance you have to have a bug. So if you compile to LLVM, you will find the bugs from the front end to LLVM IR generation. If you just go to x86 binary, you will you will probably find more bugs because you will also call the code generation from LLVM IR to x86. So you will cross even more code in the compiler and thus have more chance to find bugs in them.
So to follow up on that, are you finding more bugs in the first half where you for example, do you think it's valuable to generate more random C programs and test the LLVM IR, or would you generate random LLVM IR programs and test the second half? Would you find a difference depending on where you start generating the programs?
Actually, I'm not the one who have created the fuzzers and tested, so I can't give you that much insight into that, but I've read papers. There is a big study, the one which is cited at the beginning of the slide, about compiler bugs, and most bugs are in optimizations actually. So typically this will mainly happen in the passes over the LLVM IR. That's where you will find most of the bugs.
Right. Thanks a lot.
How hard are these bugs to fix?
What?
How hard is it to fix these bugs? I mean, you've looked at the patches and put the statements. Was it a lot of changes?
Yeah, I've not fixed the bugs by myself, but I've read a lot of reports on Bugzilla. And yeah, it really depends on the bug, you know. Sometimes they do some kind of, you have really something like, you know, from this revision of LLVM, at this revision, before this revision, there was no bug, and after this revision was applied, the bug appears. And when you have that, you can easily, okay, it's this patch which created the problem, and from that you can, if you are a compiler maintainer, you are familiar with the code, you can quite quickly find a bug and solve it. And in this case, the bug can be solved, yeah, you know, in a few hours and this kind of stuff. But sometimes, you know, I've seen some bug reports that have been reopened and reopened and reopened because someone was reporting the bug, and then, yeah, you know, nobody was able to explain what was happening. Some guys couldn't reproduce it, some could, and in the end it was closed, and then someone reported a similar behavior later, and in the end the bug was never solved, but yeah, you know, so yeah, if it affects some obscure behavior.
I'm asking about fuzzing motivated bugs and not bugs in general.
About fuzzing bugs, I think it depends. Okay. Some are very simple. Some are much more complex. You know, it's just fun stuff like that, and it really depends. Some bugs can be just one line of code. For other, it can affect one or two files. So it can be a bit more complex. Actually, the simplest bug were usually the ones found by this formal verification tool, where it was usually, as the tool was really focused on optimizations, so it was really usually one line to change in the optimization, and it was okay. So yeah.
Can we maybe defer the other questions to the break so we can move on with the program and we stay on time because it's 10 past already. So thanks again, Mike.
Okay, my pleasure.